I want to say thank you to everyone for coming to this special edition, special Christmas edition of the Haskell Stockholm Meetup. Very glad you could join us today. For those who don't know me, my name is Christoffer Ekeroth, and I'm part of Functional Software, like the company that usually organizes these meetups. And yeah, what else? You can find me on Blue Sky. I'm with the times. I changed the X. This used to be X handle before, but now I'm on Blue Sky. Yeah, and I've been kind of on a programming language theory stint lately. So I am going to subject you to some stuff that I just learned and that I'm very excited about. And just a bit of warning, this presentation turned out to be quite theory heavy. So I hope you didn't hit the mulled wine too hard before. Yeah, we have a website as well. I guess you're supposed to have that in this day and age. And finally, our sales pitch is that we help companies find functional programmers, both freelancers, and we help out with recruitment as well. If you need Haskell, Scala, F# developers, Erlang, Elixir, what have you, come talk to us. Or if you want to work with those languages, we're also good people to talk to. But yes, let's get started. So today we're going to talk about type checking, but just some quick preliminaries. What is a type checker? So in short, what the type checker does is that it looks at the terms in the abstract syntax tree. This is what you get the step after parsing code in your language. And it looks at the abstract syntax tree and it tries to figure out what the types of the different terms are. And usually it will either succeed and say this program is well typed, and it might even return a type. And otherwise it will fail. So you can think of it as a recursive function it basically goes from terms to types. And if you're familiar with Haskell, you will also be familiar with the fact that you don't need to type type annotations everywhere. And this is because Haskell uses something called type inference, which is a bit of an overloaded term, unfortunately. I think maybe it's better to talk about type reconstruction, as in you get an unannotated program and you get a typed program back. And the usual algorithm is called this mode of type checking rather is called Hindley-Milner, and it was popularized by Standard ML in the 70s. But now it's quite common. It's the most, probably the most common way to check types, except for having the programmer specify them explicitly. Another interesting property is that, at least in the basic form, it's shown to be complete, as in any valid program will actually succeed at type checking. So it doesn't matter how complex the program is, it can always infer the types. And of course you can break this in a million fascinating ways, but at least the core idea is that it should always be possible to infer the complete type of a program. And you can think of it as a strategy that has two parts. In one part, you sort of infer the constraints, or you try to build a set of constraints from the type or from the syntax tree. And in the second part, you solve the constraints. And we'll get into more detail about how those things work soon. Okay, and just to keep this, in order to not make this an entire semester-long course at the university, we will settle for a very simple language to type check, which is the type lambda calculus. And the original type lambda calculus is just functions. So, which can be a bit like, I mean, it's Turing complete, but not very intuitive. So to make it a bit more like, what do you call it? Like, well, practical, easier to understand, we will add Boolean logic and integers. And this also makes it easier to have like different types, so we can show how type checking can fail. Just to give you like a quick overview, I put some like fake language, or like, let's say our pretend imaginary language is on the left, and then we have the terms, what kind of term it is, on the right. So 5 would be an example of like an integer, true is a Boolean, and then we have a conditional, like if true, then da 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 da. Well, the x is an example of referencing a variable, and then we have a function. So this is just how you would write the identity function in our pretend language. And finally, we have function application. And if you're not used to like ML style languages, you might think, oh, he put the parentheses on the wrong side. Like, no, it's in ML style languages, or well, in the lambda calculus as well, you usually use a space to show that you're actually executing a function. Oh yeah, sorry, I forgot to mention, if you have any questions, like just shout them out. No need to wait. Okay, so the basic idea of type inference is that every term, or like every term gets assigned a variable. So, for example, if we have this conditional term here, it has 3 subterms. So we assign names to them. So the first term gets named T1, the second name gets named T2, the third one gets named T3, and so on. And then, like, this is the first step. And then we will use the rules of the type system to add constraints to these variables. And what is a constraint? Basically, it says that, like, you know, we can, how can I put it? Like, you can add these rules that a variable must follow. So, for example, if we look at the typing rules for conditionals, it says that the first term must be a what? Boolean. Boolean, yes, thank you. Do we have any other typing rules? I mean, okay, pretend you're not seeing this. Maybe I shouldn't have put this on the slide if I wanted to make it a quiz.
T2 and T3 must be the same type.
Yes, exactly. Because like both body terms must be of the same type, right? Because the conditional only has a single return type. And then, okay, so that's one set of rules that we have to impose. And I've written this out here, like, okay, T1 must be a bool. That's the first one. And then T2 must be the same as T3. So you can read this as, well, equals. Like T1 must equal bool, T2 must equal T3. But then we also have to consider, okay, what terms did we put here? So here we put the term x is in the place of T1, like the variable x. So we can also say that, okay, other than being a bool, T1 must also have the same type as the variable x. And the same thing with T2 and T3, because both of them are int literals, so both need to have this type. Or T2 needs to have the type int, and T3 needs to have the type int as well. Okay, so yeah, this is what I mean by constraints, basically. This is like a system of constraints that we can solve later. So I'm just going to walk through a quick example of like how this would actually work. Like here's something quite similar to what we just saw with another term, because like, you know, well, where did this x come from? It like just came out of thin air. But here we can say that, oh, okay, x was actually the argument to this function. So then we generate our constraints. So T1 must be equal to X, and then T2. Oh, sorry, yeah, sorry. I'm mixing my slides up. I finished this presentation at like 2 a.m. in the morning, so some things are a bit foggy. But okay, so we have this system of constraints, and we can see that, okay, this seems to like kind of work out. I mean, the critical parts are like when you have the same, like when a single variable is assigned to like multiple different things. So we can see that, okay, T2 is a bool, and then T2 should be the same as T1, and T1 should be the same as X, okay, but we haven't actually said that X must be of any other type, so that's okay, I mean, that's fine. And then we said that T3 is an int, okay, so far so good, T4 is also an int, and then we have the typing rule that says that the body terms must be the same. So we check that T3 is indeed equal to T4. And if we go back and look it up, we can see that, oh wait, yeah, they are both ints. So that's fine. Okay, so what happens, for example, if we try to feed a number into this function? Like, we can keep resolving the constraints as before, but now we have another one, an additional one that says that, so T1 was the variable, the input argument, and we unify that with bool due to this rule. So okay, X must be a bool. And then when we apply the argument, there's a rule that says that the argument to the function must, well, naturally be the same type as the function argument in the body. And we said that this was supposed to be a bool, but T5 is an int. So then we have this last unification, or this last constraint, which will fail. Because T5 and T1 were not equal, because T1 was a bool and T5 was an int. So this is an example of what happens when we can't solve the constraints. Then you will get a type error. The tricky part about type inference is that it can't know, like, which one is right. Like, did you want the function to take an integer as an input? Was that your intention? Or was it supposed to take a bool? Like, it doesn't know. And this is why sometimes, you might have noticed when you code Haskell or some other language with type inference, like, change something in one part of the program, then something else explodes, like, on the other side of the code base. But this is because it's like, it can't tell, like, it's not clear which rule it was the right one and which one was wrong. Okay, so we're about ready to dive into the implementation of how to solve this, or how to create a system like this. Just want to give you like a quick overview of the strategy that we will use, because there are a bunch of different ways we could go about this. But I think this one, the strategy we will employ now is that we will first generate all those variable names. So I don't know what this step is called, but I called it labeling. Sounded good. So first we will label each node in the abstract syntax tree, so we can assign variable names to them, just like I did in the examples. And then we will walk through the typing rules of the type system to generate constraints. And then finally, we will have a unification step, which checks that we can actually solve this constraint system. And there's a bit of like an elegant touch to this, which means that you can make it so that all of the steps prior will never fail. And Haskell programmers know what that means. Like, oh, you don't need that many monads. That's good. Like, we don't have to wrap everything in like an either monad. Like, we can just, do it. We don't, like, Haskell fans, don't worry, there will be plenty of monads. But at least now we don't have to stack them. And this makes my life a bit easier, because then it's easier to digest. Okay, but the first thing we need is a way to represent this abstract syntax tree. So, I put in like a single data type that's called term, and it has, 6 constructors. And this is the thing we will get from the parser. So this is sort of where the job of the type checker starts. And just to map it out with examples. So 5 is an example of an int literal. True would be a bool literal. If you look at the conditional, we can see that it has 3 subterms, so they're all represented here as a tuple. And then a variable is simply represented with its variable name. So we have it stores a string. Lambdas, also pretty straightforward. There's a string for the variable name, and then a term that represents the body. And finally, application is 2 terms, where the first term is supposed to be a function, and the second term is supposed to be the argument. So any questions so far?
Where do you store the types? Or maybe you will show.
Yes, we'll get to that. There's actually one property that's kind of nice about this. I mean, in a real type checker, you would probably mash a lot of information into the AST. But for this example, we will throw away a lot of stuff between the different passes, which is kind of elegant. But like you said, in a real life language, you would put a lot more stuff here. Like you would probably put the location where this thing came from, etc., etc. And we will extend it a little bit soon, but not in an elegant way, unfortunately. But yeah, so basically, this is sort of what we will get as input from the parser. So. Yes, okay, so what else do we need? We need the type to represent the variables that I was talking about before. And like you might have noticed in the previous examples, like I said, every term needs to have its own variable or variable name, with a single exception, which I will get to later. But this means we need some way to generate fresh variable names all the time. And I mean, Haskell is, when it comes to just manipulating state, depending on how you look at it, Haskell can either be the best language in the world or the worst language in the world. Either way, we need some way to carry state through this computation. So I've designed I decided to use the state monad, and I'm not a super good Haskell programmer. There's probably much better ways to do this. I heard someone say just use IO or something like that. But for this example, we will use the state monad, and we have a function that generates a new variable name. And what we do is, I forgot to mention, we use integers to keep track of the different variables. So it's like a unique incrementing integer. So this new var function, it gives us a new integer and wraps that in this var constructor, and then it updates the state. Okay, now we get to that ugly thing with the terms. So now we want to sort of to track these variables during this labeling process. We need to attach a variable to each node in the AST. So we have to sort of do violence to the elegant representation and create something like this instead. And the int literals and the bool literals, they are the same. I decided not to mess with those, because that's you can think of them as the leaf nodes in the type checking, because they can, an integer literal can only ever be an integer literal. So we don't really need to type check it. or it's trivial, so it will never need to be assigned a type variable. So I skipped that. Conditionals, on the other hand, we will need a type variable for each, we will need a variable for each subterm. So instead of just having term here, now it's var term, var term, var term. So it's like, well, pairs of variables and terms. And the same goes here for the lambdas. Like the lambda will have a variable to keep track of the input argument, and then the body term will also get its own variable. And then variables themselves, now we sort of get into meta thing, the variables. So each variable is also associated with a variable. And we will use a kind of like a trick later on. So but yeah, keep this in mind, because this one is a bit special. And yeah, as I wrote there, okay, variable doesn't have a subterm. Like, why did variable get its own variable? Well, like I said, there's a neat little trick we can apply here to that leverages the fact that we're doing tracking constraints. And again, application, it was 2 terms, so you also replace those with pairs of variables and terms. Okay, so, and the L is supposed to stand for labeled, so labeled in literal, like a labeled conditional, etc., etc. There's also a cool trick that you can use. There's a paper called Trees That Grow that can help you manage like this. Because this is just one pass. Imagine, for example, if you want to store more advanced type information, or have multiple passes. It's untenable to create, or also imagine that they have more different types of terms. It would be super annoying if you had to create one term for every compiler pass. But there's a cool technique in the Trees That Grow paper that you can use if you want to implement this yourself. But yes, this is not ICFP, so we won't do any paper presentations. Okay, so let's start labeling. So as I just mentioned, we can skip labels, we can skip labeling literals, because they're only ever equivalent to one type. But we still have to keep this label. Oh yeah, sorry, we introduce a label function. Forgot to say that. So the label function simply takes a term and outputs a labeled term. And because we're in the state monad, we have to do pure here, even though we just want to represent or return simple values. Okay, so that was simple enough. Conditionals are not that complicated either. We generate 3. I should mention okay, so now in the do notation, we generate, or in the do block, we generate 3 variables, 1 for each subterm. And then we also need to recursively keep labeling the subterms as well. So we have these 3 input terms, and then we label them and call them T1 prime, T2 prime, etc. And then we simply return the pairs of variables and subterms. Any questions so far about this? Good. Okay, so now comes the trick with the variables. So one thing you can do to make your life a bit easier is you can introduce a rule that says that if you've seen a variable before, you should reuse the same, this gets a bit complex. So if you have seen a variable term before, reuse the variable that you used previously. So this means that as soon as we get if you see a variable term twice, we will reuse the same variable for both terms.
But the same shadow, if you have a nested lambda with the same parameter name, then the later one will shadow the previous one. And they can have different types.
Okay, yeah, that's a good point. Like if you have, if you can accidentally shadow another variable, if it, but no, but then it will fail during unification.
Because that is valid, I think, at least in lambda calculus. But I guess you can rename the variables in like previous part.
Yeah. Ah, so you did want to shadow, or you didn't want to shadow?
I think in standard lambda calculus, it's okay to shadow. Like you can have a from x to x.
Yeah. You could shadow here as well, but then then it has to have the same type.
Yeah.
So yeah, depends on how you want it to be. I guess you could call it either that bug or a feature. But yeah, so the important point to get is that okay, so if we've seen the same variable term before, we should reuse the same var. Let's see. Oh yeah, and then another trick. So I said before that we didn't want this pass to fail, because basically the first labeling pass can't fail, except in this one case. So in order not to like dirty up the whole code by putting it in like an either monad, we can say that, if you use a variable that hasn't been defined before, we return a special term undefined instead. And people might say, oh, that's a bit weird, but if you call it the bottom, it's okay. Trust me, I've read the papers. Real scientists do this. Let's see. Okay, so that was variables. And labeling functions is also quite basic. We generate two new variables for the argument and the body term. But again, the special part here is that I forgot to mention something. The symbols is a table of variable terms that we've seen before that maps variable terms to variables. So now we have to add this argument to the labeling function, and we use this to track the variable terms we've already labeled. And so functions, like I said, is pretty basic, except for the fact that we need to update the symbol table with the function argument that was introduced. But yeah, then we update the symbol table, and then we recursively label the body term as well, and return the lambda or a labeled lambda term. Okay, any more questions so far? No? Okay, we're almost done with the labeling. Then we can get to the fun stuff. So function application also, that's also pretty simple. Just generate variables for each variables for each subterm. Recursively label the subterms, and then return a labeled application term. Okay, so now we've come to the second step, which is to generate constraints. The first thing we do is we extend our types with a new type. Now we get into this meta stuff again. Anyway, so the type has 5 constructors for ints, bools, functions, and a special one, like type vars. So the special thing about type inference is that we let variables can also be can be treated as a type, and it represents a type that we haven't figured out what it is yet. So this makes the type inference algorithms a bit special. And also we throw in an undefined here to treat the case where we return an undefined during the labeling step. Let's see. Okay, so the infer function takes a variable and a labeled term, and then it tries to map the type variable, or sorry, then it creates a mapping between this variable and a type that it has figured out. And so this is sort of this is how we save the constraints. So it's like tuples with variables as the first element and then a type as the second one. And like I said before, variables, there can be variables on the right-hand side as well. But we've wrapped them in the type var type. Okay, so now we repeat the same thing again, but now for creating constraints. So we start with the literals. And again, literals are quite basic. So we forgot to mention that we create an infer function that takes a var as an argument, like I said. So the infer function for literals takes the var and then outputs a pair with the literal and the literals type. So for int literals, we return a var int pair. For bool literals, we return a var bool pair, etc. And undefined has basically the same rule, like we just return undefined. Okay, so now we implement the rule for conditionals with constraints. So we get if we get one of those labeled conditionals as input, we know we'll get like 3 pairs of variables and terms. So we say that the first one, the first variable must have the type bool, and the second one must, or the v2, the second variable, must, let's see, what the hell did I type there? It must be equal to the variable 3, which represents the second body term. And this is how we can tell the how we can generate a constraint that says that they must be equal. And notice that we need to wrap v3 here in a type var. And finally, var is supposed to be like the return type of the conditional. And we unify that with, we can't pick any of these, type var 3 or type var 2, because we know that those must also be equal. And then finally, we recursively infer the types of all the 3 subterms as well. Okay, so if we want to generate rules for lambdas, like the return type of a lambda is, what did I type there? Oh yeah, sorry. If you have a lambda term, we know that it should unify to a function. And the type of the function should be, like the output type should be the same as the input type should be the same as the first term here, because that's the input to that's the argument to lambda. And then the the output type of the function should be the type of the body term. And notice that like functions are a bit special because they contain types themselves. So we need to treat them a bit special, like when we solve the constraints later. Oh, sorry, I put this twice. Okay. But yeah, so there's a bonus one here. So variables are also quite simple. We just return the type variable that was associated with the lambda. Okay, application is a bit more interesting because now we have a bunch more like typing rules. So we know that the first term in an application must be a function. And now we use the fact that the functions also contain types, because we know that the input type to the function must be the same as the argument in the application term. So we unify these two, and then we know that the output type of the application must be the same as the return type of the application is var, which is like the type of the entire expression. And then we need to recursively infer the types for both the input, the lambda term, which is supposed to be a function, and the argument term. So any questions so far? So anyway, this is what it takes to generate our system of constraints. So after this, we're ready to move on to unification. So basically what unification does is that we have this list of mappings between variables and types, and then it tries to build something that's called a substitution mapping, where we sort of try to solve this set of equations and also maintain the decisions we made before. The key part to remember is that once we've seen a variable and unified that with a type, we can't go back and unify it with another type, because then the whole step fails. So, and we represent this as a map, which maps, essentially maps, it maps variables to types, but it actually makes our life a bit simpler if we can have types on both ends of the tuple. So we will actually, prior to doing this, and I didn't show that step, but we map all of the, if you remember from previously, we always have a variable here on the left side. But prior to the unification step, we map those to types. So it's type and type in the tuples. And then now we also need a special case for undefined. And the undefined will not unify with anything. And like I said before, I can show you the code. That's easier. Okay, so basically this is the most simple unification function. So like I said before, it takes two types, basically. Then it outputs this substitution map, which is a mapping of variables to types. And again, the most basic case is that both of these both of these types are equal. Then we don't need to do anything. Okay, you said that an int is an int. Fair enough. No objections. Then we also have the special rules for undefined. And then as I mentioned, this is the part that actually can fail. So we return, and we have an either monad here. So if we run into undefined, for example, we just return undefined. And left, so it's an error. And also we will add a bunch of stuff in between these cases, or rather we will add stuff here. But if you can think of this as the base case, it's if basically if two terms are not equal, they can't be unified. But there's more to it than this, as you might have suspected. So here comes the trick. If we see a variable, then we try to substitute that, or we try to resolve that variable. So we look in the previous substitutions that we have made and say okay, did we make a substitution for this variable already? Did we already map it to a type? And to avoid like a common bug in these kinds of algorithms, we actually try to resolve both sides. So we start with the left side, which we've already deduced was a type variable because we match on it here in the function head. But if the second one is if the second one is a type variable, we also try to look that up. So we have two attempts, res1 and res2, to actually resolve these two variables, like mappings that we have already seen. And if we have actually unified, or if we've actually seen this variable before, we do a recursive call to unify with the type that we found. So t prim here is like, okay, let's say a variable x was mapped to int, then we get an int here and we rerun the unification with int instead. And like I said, like we do the same thing for if the other side, if you could resolve the other side to a, or if you had already seen that one. And basically we have another like case here that flips the arguments, because we want, it shouldn't matter which of these two types are a type variable. So in order not to have to implement the same algorithm twice, we basically just call this again, but with the arguments switched. So we always get the type variable as the first argument, because then we only need to cover one case here. And the final thing is like, okay, what if there was no variable, or sorry, if we hadn't seen this variable before, then we save it to the substitution map. So basically, the first time we see a variable, we save it, but if we see it again, we will like fetch the type that we found the last time. And this is sort of the whole core of the unification thing, because this is usually what can actually make it fail for non-trivial cases. So basically, you can think of it as recursively trying to resolve all of the variables until you only have like two, types next to each other, which can either be either they are the same or they are different. And if they are different, the unification fails.
If you have like two type of variables, you need to unify them, then you will have an infinite loop.
Yes. Yes, very good. So if you like, there is a risk of running into an infinite loop here. Yes, and there's a remedy for this. But before we get into that, there's one more thing we need to think about. And that is like as mentioned before, if we have a function type that's actually, basically has nested types. And functions will only unify with other functions, naturally. And this is we have to remember to put this case close to the bottom. So we need to resolve all the variables first, and then we put this case below the variable. So if you have anything but a function on both sides, we should fail unification. And then we just grab the two types from each function and recursively unify them both. So in one, the first input type and the second input type, they need to be the same. The output type and the output type 1 and output type 2 also need to be the same type. And just like you mentioned, what happens if we have a recursive definition somewhere? Because you could write something like x is equal to x, or even more subtle, you could have x on the left-hand side, and then somewhere in a subterm on the right-hand side, you have also have an x. So that would create an infinite loop. But in logic systems, you usually have something called an occurs check. that actually loops through the whole thing and checks like, okay, does X occur in some subterm, like when I try to create my substitution. So basically what you do is just before you, or if you see a new variable, before you insert it into the substitution map, you perform this occurs check, just to check like, okay, is this in here or not? And this is not like super efficient because you have to, like, there's probably a much faster way to do this. You can probably cache type info, because every time it needs to like traverse the whole tree of terms. There's probably like very cool papers about how to do this efficiently. But yeah, that's the whole thing. Actually, it was actually when I started this, I thought it would be much more complicated. I also thought I would be able to fit it into 30 minutes instead of the 45 minutes that this presentation took. But still, it wasn't that. Or what do you guys think? Was it?
Do we actually handle polymorphism?
No, that's another good point.
If we have a function x to x, this cannot type check because.
Yes, yeah, this is a very good point. Like, so what about polymorphism? And let's see, we had the identity function here, close to the start, I think. Yeah, there we go. Oh, sorry. I need to realize that I have the presenter view with 2 slides, so you're not seeing what I'm seeing, which is this. So, okay, what type should this have? X to X. And the somewhat disappointing answer in this type checker is that it will have whatever type it runs into first. So basically you need to do some more tricks to make this type system polymorphic. Because, single function argument can only unify to a single type. There are, I think the process is called Scholemization. So if you have basically Scholemization is when the type checker looks at a function like this and basically deduces that, or rather like this, if it finishes type checking this function and it notices that, oh, I didn't unify X with anything, that means it could be anything. So basically you would turn this into a type variable. But also, again, now you notice why this is kind of like hard to talk about, because type variables was also the thing that we used to unify in the type checking step. So yeah, you have to sort of be careful when you talk about these things. But yeah, anyway, there's lots of papers have been written about like how we can combine unification with polymorphism, because sometimes it can be quite tricky. Like you probably want something like universal, or what's it called, like quantification. Yeah, never mind. That's the topic for another talk. Let's see. Oh, sorry, the last slide. Oh, thank you.